Everybody, let's take a minute and relate cell potential to equilibrium. Okay. I actually like cell potential and equilibrium because it's kind of like the go-between. It's one of the go-betweens. Okay. You can talk about how cell potential goes in between thermodynamics with delta G. And in this case, we'll talk about how cell potential relates to equilibrium, and I think that's cool. So at equilibrium, remember that delta G equals 0. The point is that the reaction is neither spontaneous forward nor spontaneous in the other direction. It's just sitting there. And I don't want to say that it's just sitting there, but the net change in the reaction is nothing. And so that means that the delta G is 0. Okay. And so because the delta G is 0, let's see. Remember, delta G equals negative NFE, okay? And so because the delta G is 0, keep in mind that the non-standard cell potential, just the E, is going to be 0 because if this is 0, N has to be a number, F has to be a number, so E has to be 0. But it's important to know that as things react, the concentrations of everything is changing. So because once it reaches equilibrium, we're saying that it's at a non-standard equilibrium. So the idea here is that non-standard potential energy is 0. And then we can use the Nernst equation, and then we can rewrite the Nernst equation to give us this reaction. Okay, and so let's take a look at iron plus cadmium reacts to form iron 3-ion plus cadmium solid. Okay, so let's split this into its half reactions. Fe reacts to form Fe 3 plus 3 electrons, and then we have 2 electrons plus cadmium 2 plus reacts to form cadmium. Okay, and so this isn't a video on how to balance these. If you want to go back, you can watch that video, or if you want to find it, you can find that video. Remember, this has to stay even, so this is going to be a 2, and this is going to be a 3. And so now we have how many electrons are being transferred. So in this case, I'll put it in red up here, N equals 6 electrons, or 6 moles of electrons. Okay, and now the other thing we need is we need the cell potential. So the cell potential, remember, is the cathode minus the anode, okay, and it's the standard cell potential, the E0, okay. So I'm going to go to my list of cell potentials, okay, and I'm going to look for the iron going to 3 plus, okay, Fe3 plus, oh, that's only 1 electron, that doesn't get us anywhere. Okay, so let's go down somewhere. We have to have it, this was Fe2 plus going 2 electrons. That doesn't help us. Okay, let's see. Somewhere on here I have to find iron, Fe3 plus, okay. So why isn't Fe3 plus on here? Fe3 plus. Okay, well, I do have cadmium. That one I know I have. So cadmium is here. So this is 2 plus 2 electrons is negative 0.40. So let's go there. So this one, 2 plus 2 electrons. So this is minus 0.40. And now this, I'm going to pull up a different reduction potential. So give me a minute and I'll do that. So I just did a little search. So the reduction potential, at least that's what Google's telling me, okay, is negative 0.04. Okay, so we will go back to our thing here. And so, whoa. Oh, you know what? I'm going to go like that. Look at that. Okay. So this is this one is negative. Let me get rid of some of this stuff. Okay. So it's negative 0.04, negative 0.04. So that's for iron. And what did we say iron was? Get rid of some of this stuff. Okay. Okay, so iron is being oxidized. So that's our anode. So it's our cathode minus our anode. So cathode is this, so it's negative 0.40 volts minus a negative 0.04 volts. And so this is equal to, and let me pull up my calculator. So it's turn it on. Hey, look, electrochem. So it's negative. Better clear that out of there. So it's negative 0.40 minus a negative 0.04, and so that's going to be so the cell potential, I'll do it in red like this one. So the E naught cell is equal to negative 0.36 volts. Okay. So that's going to be a non-spontaneous reaction. Okay. So that means the reaction isn't going to be spontaneous in the forward direction. It's going to be spontaneous in the reverse direction. So that's kind of interesting. But let's do this. So we do ln of K equals N, which is 6, times negative 0.036 divided by 0.0257. And so that equals, let's see, so let's see, I always touch my calculator and then it's bad. 6 times negative 0.36, okay, and then divided by 0.257, and so we get negative 84.0. Okay, now we have to delog this. So when we delog this, so now we have that's the lnk. So we want to do E, and we do E. Okay, so we're going to go E to the negative 84, and we get an answer that K equals 3.31 times 10 to the minus 37. Okay, so that's a really, really tiny K. Okay, and that makes sense because this is a non-spontaneous reaction in the forward direction. And so this, when your K is this, remember K is products over reactants, that just means that this has way, way more reactants than products. So life is pretty cool. Okay, so that's how we use cell potential to get us into equilibrium. And have a great day, everybody.